Okay, so my name is John Reagan. I'm the compiler artist in residence at VSI. I've started with compilers. I joined the digital compiler teams in 1983. So I've done this for a year or two. Okay, talk a little bit on the updates. I want to give, and so I've given this presentation, these next couple slides, several times in the past on how we got our compilers and the operating system Bootstrap from Itanium and Alpha to x86. You're a special crowd. This is the last time I'm going to show these slides. I am tired of showing them. So if you haven't seen them by now, this is your last chance. Tell your children, because this is it. So on Itanium, we have a set of compilers. I'll call them legacy compilers, C++ is special. And they've always interfaced through a digital proprietary backend we call GEM. It's not an acronym, it's just GEM. All those front ends generated intermediate code to GEM backend. It does the optimization, code generation like your compilers do. Right. And so when VSI found me, they knew where I was at. To do compilers for x86, I was sitting with Claire Grant in a room somewhere. I think we're in a Panera coffee shop. And she said, how would you do this on x86? And so I said, great. What I'm going to do for x86 is, here's some back-end history on that. We're going to have to pick a different back-end, not the GEM back-end. GEM was old and legacy, written half in Bliss, 2/3 in Bliss. We don't have a lot of Bliss programmers left. I'll talk about Bliss later if you want, or on the bar later if you want. But what to do first, I needed to do something. I didn't want to recode every front end. I didn't want to pick up back end that I'd have to make changes to, well, some. So I had some experience. I had previously worked in Hewlett Packard, and after working in VMS for many years, I spent a couple years working for HP Nonstop. So at the time, Nonstop, if you haven't noticed, has also been ported to x86. I was in charge of the back end for the x86 Nonstop work. So what we used there, I said, we used a different back end, I said, but we're going to use LLVM for our compilers for x86. LLVM is a known quantity. It's highly supported, large community of active development. So instead of me having 10 or 20 developers, I essentially have 200 developers working on LLVM. But 200, I hope they do the right thing. I think on targets that sometimes we don't care about. So the simple one was just write a converter that converts the GEM intermediate into LLVM intermediate. All those compiler front ends, again, C++ is different. All those other compiler front ends still think they're talking to GEM. They generate every data structure they've ever generated. So those front ends are essentially untouched. So that's how I can guarantee that your legacy COBOL, Pascal, Fortran, C moves forward because the front ends didn't change. So, for this whole porting to x86, if you have one of those languages, as I think if you were in Norm Lastovica's talk yesterday, though there was just a few. Sorry, no. You heard that most things just recompile and go, and they honestly do. If you don't, it's one of my compiler bugs, but it's usually a bug in that converter. The only really new piece of code in this picture is that little box that converts GEM intermediate to LLVM intermediate. And so whenever a bug comes in, that's where I assume it's in that piece of code, and it almost always is. So I'll talk a little bit about, maybe macros a little different. I'll talk about macro later. So how did I have to do GEM to LLVM? That piece of converter code. I just had to map all the GEM intermediates to LLVM intermediates. I'll let you read that. The only part, when I came up with this in my head, it's all worked out mostly to plan. Long double has been a challenge due to the older LLVM I used for the cross compilers. But the other one was static data initialization, Fortran comic blocks, COBOL initialization, some Bliss constructs had proved to be actually rather tricky to do with LLVM because they're more geared toward C, C++, Swift, those type of languages. Then there's things unique about VMS. I had to teach the LLVM backend. I can't just use the one off the shelf. I go grab the Linux LLVM for a 64-bit system, except VMS is weird. We're not a 64-bit system we put code in 64-bit space, but the stack's still in 32-bit space. And we have this, some people love descriptors, some people hate descriptors. I guess I'm in both camps. What I hate about descriptors is they expose 32-bit addresses to you. You have to fill those in. So you have a string somewhere, you have a local variable, you want to make a string descriptor to it. You better have a 32-bit address, which means I had to keep data in 32-bit space. I had to keep stack in 32-bit space, but I want to put code in 64-bit space. And if I try to describe that to a Linux programmer, their head explodes. They go, why would you do that? And it's because I'm stuck with all these interfaces that have 32-bit addresses on them, and I'm also stuck with macro code. I can go into a C program, change a couple type defs at the top, and turn all my 32-bit things into 64-bit things, at least if it's well-written C, and you can insert a joke there if you want. But if it's well-written C, you can easily change data types. Not so in macro, right? If your macro programmers, all the instructions you use have these size implications. You do a move word, a move long, a move quad. So if you want to change something from a 32-bit thing to a 64-bit thing, you have to not just change one definition, you have to change every single instruction that touches it. And no one wants to do it. So that's why it kept me 32-bit stayed 32-bit. A few other ones I want to point out. The calling standard we use for how you pass back and forth. We have stayed really true to the AMD documented calling standard, the one that everybody uses on Linux. So in the industry, there's essentially two different calling standards on x86. We've got to keep at least 64 bits x86. There's the one that Linux uses, and there's one Windows uses. And so we did not pick the Windows one. But the only other one that was interesting is that on VMS, every call has an arg count. On Linux, you call a routine. If there's 3 arguments, there's no 3 anywhere. The call routine knows there's 3 because it knows, right? There's no way to check that. So we had to add that in. There's a few things we've added in an upward compatible fashion, but what this let me do, and we may talk a little later in a second about cross-comparison bootstrapping, you can take a Linux.o file, x86, bring it to VMS, our linker taped. You couldn't do that on Tangen, but you can do it on x86. And that feature was added for me, not for any of you. You can use it if you want, but the reason I did it is this next slide. I had to bootstrap these things. And so where am I going to build these very first compilers? I needed, at the time, we didn't have a running VMS x86 system. I needed compilers that ran on VMS Titanium that generated x86 code. That x86 code comes out of LLVM. I have to build these things somewhere. So very first, I built the cross compilers on Itanium using the Itanium C++ compiler, which is barely C++03, but it's barely. So I got a back end, I got the legacy back ends. I mean, the front ends, everybody compiled pieces everywhere. But how do I want to get the native C++ compiler? I didn't have a cross C++ compiler. Trust me, I tried to take Clang LLVM and shove it through the Itanium C++ compiler. It wouldn't fit. There was too much weird C++ code that our Itanium compiler doesn't handle. So we had to build that Itanium compiler, the native C++ compiler, by compiling it on Linux with a special cross compiler. We took the Linux Clang compiler, modified it to generate VMS objects, remember, called arg count and a few things in the object file. So I have a Linux hosted compiler that generates essentially OBJ files that I then have to drag over and take to and link on VMS. They're not OBJ files, they're just most straightly .o files. So we link them all over, bring the O files over. So I have Linux generated object files I have to link on VMS. And that's the only reason the linker takes them. Let's see what else I want to talk about here. Right. So all our compilers now, except for C++, always different, they're natively compiled on VMS by native compilers with full optimization turned on. So you can imagine by bootstrapping, the first generation of native compilers were built with cross compilers, usually Bliss or C, bring them over, link them either with a native linker or a cross linker, and then that very first compiler I used then to build the compiler again natively. The first time around was no optimize. Then you do that, you compare it again, run your tests, then you build the compiler yet again with that compiler with optimizations turned on, then you run another set of tests. It sounds complicated, but if you're here for the last talk, it's easier than building a Volvo car. It's not as long as you keep track in your head which piece is which, the native cross stuff and where directory you're in, which environment you're in, is a little mind-bending sometimes. But the optimizers are there now. We're still doing a little bit of tweaking on the routine inliner, matching it how it kind of worked on Titanium or didn't. But the LLVM inliner does a pretty good job. And there's some places in LLVM that if we gave it additional semantic information about the program, it can do a little better pointer analysis and a little better optimization. But for the most part, if you had to say percentage-wise, we probably have the optimizer turned up to 8. We can squeeze a little more out of it, but it does quite well. We've done some crude performance testing between no optimize and optimize, and it's a substantial difference, right? I'll probably talk here, we mentioned since I'm on this slide, I don't think I have another, about performance stuff. Again, in Norm's talk, we've talked about some of the system performance. One of the things we did recently, some of the low-level routines that we've been using for memory move and string searching. On every platform, they've been tend to be written in native assembly, hand optimized alpha on alpha, Titanium, x86, just to bootstrap the operating system. I have a bunch of reference routines, just either a straight C or straight Bliss. And if you're looking for a character in a string, it looped over the string one character at a time. It got the job done, but it's not very efficient. And that's kind of what we had left in the operating system, sometimes intentionally, sometimes, oh crap, I left that in there. I wanted to rewrite that. So probably for the next update, either this summer or the 924, we've rewritten all those low-level routines in x86 assembly, using instructions that Intel themselves said, this is the way to use them for better performance. There's an entire Intel optimization guide on their website for compiler coders. So again, if you're bored some night, download that manual from Intel and read through that. Or you can read through the calling standard. I'm talking tomorrow about the calling standard. So if you're interested in that talk, please choose else, go somewhere, but I'll talk about the calling standard. So a quick thing about all the compilers, I'll stop on C++ in a minute, is we have, that's pretty much the whole set, including we added, you can actually get an x86 native assembler if you choose to do that. It's actually part of LLVM. We just repackaged the tool. But most of the stuff we've been adding versions at this point, it's been minor bug fixes. They work pretty well. The big thing is still we're focusing on debugging. Again, I think we've seen a couple references already. The challenge was our debugger was just very accustomed to the dwarf debugging that came out of the Titanium compilers. When all of a sudden LLVM presented it with a lot more dwarf in a lot of different combinations, our debugger did not like that. So there are places where we had to make the debugger smarter. And then there's also places where the LLVM we're using had no idea about certain things in COBOL or Pascal or other languages. And if we can just get the right debug information to come out the back end, the debugger would be fine. So now we're battling that issue too. We're trying to get the back end to understand more about these weird legacy front ends. I think we probably aren't the first ones with a COBOL or a Pascal attached to LLVM, but I'm pretty sure we're the first people who put a basic on LLVM back. I did give a few talks on these a couple of years ago at the LLVM conference. So they video all their sessions. If you Google me, you'll find those talks. But there's the only one I wanted to point out in particular, again, if you're macro users, the macro that has been coming in since it's bundled the operating system, the 19.3 update 1 that just came out. The macro in there is, at least from a debugging point of view, substantially better. And Antoine's in the back, he can wave his hand if you want to talk macro, you'll find him later. But that's probably an important one there. And the debugger is better in update 1. Each of them are making incremental changes. I've been using it now myself to debug things. Every now and then I can still get a step to mess up. It'll get confused. Again, the data structure that the compiler generates to tell the debugger which instructions belong to which line is sometimes confusing, at least to the debugger. Again, on Itanium, the way out of that data structure that the gem backend generated was straightforward but sometimes bloated. LLVM tries to be cute, and they take every little shortcut to try to generate the smallest debug line table, because there's places in the spec that says, well, if the compiler doesn't say this or this, then you can assume something else. And the debugger was just like, nope, you got to tell me. I said, no, you're supposed to be able to figure it out if we don't tell you, and we're looking for that as well. So we have a debugger person here. Where's this our Tom here? We should raise his hand and we can track him down. You can chase him down. If you have a debugger problem, you can chase him. So the compilers are straightforward. The debugger, I think I already talked ahead of myself, and these are the things about the debugger we're working on. The debugger is complex. You think it's pretty simple. It's not. It's hundreds of thousands of lines of code. It's the biggest condition handler you've ever seen. Again, I talked a little bit about macro. The one thing about macro, again, if you're certainly for performance reasons, including us, the macro compiler on previous architectures, obviously VAX macro is the VAX instructions. Alpha macro, the compiler generates some really good code. On Itanium, it does reasonably well given the Itanium architecture that it has to work with. On x86, so one of the first things reporting, what happens when you don't have enough registers? x86 has the 16. Some of them are pre-dedicated that I can't touch. So how do you fit the 32 registers that the macro compiler exposes to a lot of code, including the operating system code? How do I put 32 registers into 11 places? You can't. I tried hiding them in XMM registers. I tried thinking about how to, put two together. We'll exclusive OR them. We'll do something weird and try to kind of encode them. No, we gave up. It's like, we've got to put them somewhere. They look like machine state. I have no more room on the machine, right? We can argue there are some future Intel extensions that's supposed to give some of the future chips 32 registers, and we're not waiting for that right now. So all those alpha registers aren't registers anymore. They're memory locations. Every place, if you're a macro programmer, you touched what you thought was a hardware register. No, I had to fetch it somewhere, do some operation on it, and put it back. And where do you get them from? Well, it's not just static memory locations. They tend to be per mode, per thread, per whatever. So, your registers aren't my registers. So it's almost like any other machine state. So it's managed by the operating system. When exceptions happen and interrupts happen, they have to also be saved and copied and moved around. So if you wrote macro code before thinking that you can do better than a compiler, you're not going to. Now, of course, my argument is that we're reading and writing these things. The cache saves us. Right? If you go ask Intel and look at their price sheet, the expensive chips aren't the fast chips. they're the chips with the cache. So that's and every Linux machine on the planet, they're the GCC compiler. You compile your C code. All it has is a handful of registers and the stack. And all of those variables you have in your C program or your C++ program end up on the stack anyway. It's fast because the top of the stack eventually gets into the data cache. So I don't think it's any worse than that, but there's memory references in there. So if you think you can write macro to squeeze the best out of the hardware in x86, no, but it doesn't suck bad, but there's no benefit to writing macro for that. Anything is so it was a challenge to do this, but it works fine now. I mean, we compiled the whole operating system with this compiler, so at least the macro parts. Right. So we talked before, well-written code works fine, but what happens when we have not well-written code, which is probably the majority of code that we see, is the non-well-written code. We've talked about this before. If you have knowledge of the hardware, the calling standard, you already knew this coming from Alpha Titanium. But if you have code you didn't know and you start seeing weird missing symbols, most of the symbols we intentionally gave them different names, each architecture. So if you use one in your condition handler, you're looking for some field in some target specific data structure, you'll just get syntax errors. Missing symbol names. That's usually a hint that you've done something target specific. Or if the routine has the word handler in its name, you probably put something target specific. But the ones that I think, if the uninitialized variables catch us for bad code, but the one that catches us the most, and probably your code as well, on Alpha and Titanium, the backend alignment was relatively important. So the backend says, well, we'll fix that. We will put every variable in its own quad word. Memory's cheap. And so all these 32-bit stack variables, you have a bunch of integers. Look at how gem generated code. They're not next to each other. They're usually in their own quad word. So it's 32-bit integer alignment hole, 32-bit integer alignment hole, so far on the stack. And so what happens if some piece of code accidentally wrote 64 bits into the 32-bit variable? Well, they wrote that and they wrote over that next alignment hole that no one really cares about. Yes, on x86, we have to squeeze them all together. There's no benefit to add alignment holes. So now what happens when you wrote 64 bits over your 32-bit variable, you wrote on something that's important. So that's probably the one that I've seen most in our code and in customers. C++. The things in my nightmare. So C++ on Titanium is an older C++ compiler. C++, I said 03 at best on a good day. The standard template library on Titanium is from Rogueway, which doesn't exist anymore. I think it's an obsolete company. We don't have a license for it. We don't have a license for the Intel compiler to move it to another platform. I haven't. Even Intel is converting their compilers to LLVM. So I would try to get something. No, let's go pick an industry standard compiler that is, well, modern standard compliant. I mean, I've been getting hit for years on John, your C or C++ compiler is ancient, out of date, doesn't conform to the standards. I have new code from open source I want to bring to VMS, and your compiler doesn't like it. So, okay, fine. Here, have a full standard Clang compiler. We're going to bring it over. So our choices were Clang or GCC, and Clang has comes to LLVM, so it's a package deal, much better license. I've avoided anything dealing with GCC, both for the license, and those people are crazy. If you go to one of the newer GCC message boards, I mean, I didn't need, Linus could yell at his own people on, but if I didn't want to be involved in any of those discussions on how to tweak GCC to get something for what is essentially a proprietary operating system. Over there, you're either all in with the open source or they don't talk to you. So Clang it was. So how did we have to worry about Clang? Clang out of the box on 64 bits. The very first one we did, pointer size 64, long or 64, just like every other 64-bit compiler you'll find in the Linux world. Okay, there's your industry standard Linux compiler until we couldn't even compile our own code, right? It was, guess what? Remember those 32-bit pointers and all those VMS system interfaces? I couldn't just have variables with, that would be, yes, they're on the stack, but from Clang's point of view, the addresses are 64 bits wide. I can't take a 64-bit pointer and jam into a 32-bit script. Static data had to be made sure we did. Clang had to do the same tricks, though it's all inside the LLVM that we did for the legacy compilers. But some of the changes we still have left with is pointers are still by default 64 bits now with C++. They're still 32 bits by default with C. So if you have a mixture of C and C++, you sometimes have to watch that. And so that's what we had. Like, oh, I can't just be 64 bits everywhere. I need an option to put it back to 32 bits. So we had options to put, pointers back to 32 bits, other things to 32 bits. We added all those weird pragmas for dual pointer size. Again, the whole industry thing, I go to LLVM and say, can I put dual size pointers into your Clang front end? They go, what? I mean, there are some platforms that have them, but you're either a 32-bit Linux box where everything's 32 or a 64-bit Linux box and everything's 64. Why would you want to mix the two? And I explained to them why I want to mix the two, and they still think, yeah, that's strange. But we were able to do it. It does actually, Clang is actually pretty easy in that sense to manipulate. The thing that we are still missing and no one's complained about yet, it doesn't have VAX floating. The Itanium C++ compiler has some support for VAX floating. I never found a single user who used it. I think anybody who's smart enough to use or dumb enough to use C++, it's open source stuff. No open source code needs, VAX floating. And it's only if you had binary data on a disk, and those people who played with binary data on a disk have legacy code. It's the Fortran program that did it, or the COBOL program that did it. So no one's asked. I think with sufficient fear, and you can write a C++ class package to emulate VAX floating if you're careful, but don't. And then we also provide two compilers. Our very first internal field test compiler, it's the Clang one. It had a Linux, the Linux command line with its 550 options, I think is the last number of time I counted. But every so I have DCL command files, I have make files that have CXX commands in it. So we give you the same compiler, literally the same compiler twice. One has a DCL interface on it, one is the traditional Linux one. You can use them both. They generate the same object, the same code, there's no difference. I think even the defaults are the same. So again, if you want to switch pointer sizes, we've invented Linuxy options that you can put on the Linuxy interface to select pointer size and stuff like that. The whole names, I mean, this VMS traditionally we chop external names off of 31 characters and uppercase things because that's what VMS did. Well, open source code, people said, oh no, I have long names and I want long names, and we added long names. So the compiler has no length limit on external names. The linker doesn't care. The linker really hasn't cared about simple names in a long time. The librarian cared. So we made some changes to the librarian. We made some changes to the librarian for Unix weak symbols and VNS weak symbols. It used to not handle those. But no, you can. I think I only tried one that had like 1,000 characters in it. So that gets you a C++, because I don't have a slide, we talk about it here, I think. That gets you a C++ compiler. Well, Clang's also a C compiler. It's also an objective C compiler, but I'll ignore that part. But it's also a C compiler. The Linux command line, you do, Clang with foo.cxx. It's in C++ mode. You do Clang foo.c, it's in C mode. It doesn't know about C. There's no C++ syntax, but it now enables C11 and C17 syntax. So you get a C11 compiler out of it, a compiler. You don't really get yet all the stuff you might want in an RTL or the headers for C11 or C17. So you can easily use Clang as a C compiler, push much more modern C code through it. If it links, you're probably okay. But I think we're still working on adding some stuff to make that Clang as a C compiler a viable option. But there are people with code that wants to push it. So that gets me back to how do I get a more modern C and C++ compiler in the system. I use the same Clang. The very first C++ release didn't have what things like, we didn't have listing files. Who wants to, no one uses listing files in Linux. That's a stupid concept to them. I said, wouldn't you want to have a file that showed everything the compiler saw? The command line, the macro expansions, maybe even a capture of what the generated code was. You can archive that and use it and reference that. And people are like, no, I don't want that. I'm going, so we do. So we added all that. We may give it back to the Clang development organization, open source. They don't seem to care about it. I was at an LLVM meeting. I said, we have this thing. I'll show it to you. Do anybody want to use it? And no. So one of the mistakes we made a long way for development, we were developing, we needed to port not just the compiler, but the two RTLs that went with the compiler. And we wanted fast turnaround. And so I did the cardinal sin. I shipped RTLs in those early compiler kits. And so normally language RTLs come with the operating system. Like Fortran RTL comes, you install VMS and you get all the language RTLs, whether you need them or not. So you have them all there. So some third party, Oracle or somebody, writes some code, and all of a sudden it needs the basic RTL. It's already on your system. Not so much with the C++ RTL. So it took a while to get that onto the right version of VMS, and to get the right ownership of them in PCSI. If you've never written PCSI kits, consider yourself lucky. There's the PCSI and the operating system keep track of who owns what file. VMS install is easy. You just dump some files in the system and hope for the best. PCSI tries to be smart about it, and so it keeps track. But we did it in such a way that when you upgraded like to 923, PCSI says, oh, you probably want to keep the old ones that you had from your old field test compiler, right? And say, no, I didn't want that. So on the latest C++ compiler, there's a little additional PCSI kit inside the kit. Sometimes you have to run a little thing to upgrade PCSI itself. There's a little one here called CXX Fix-Up, where you run it and it fixes up all the RTL word dependencies, and you do that. But we can't do it in the compiler. It has to be a separate kit. I won't bore you with the details. But once you do that, going on forward, the RTLs will come in the operating system like every other RTL. Until I have to change my mind again. But at this point, it's a pretty reasonable C++ compiler. I mean, it's all Clang. The RTLs are pretty good, though I think if you can easily do C++11, C++14 with this compiler. If you go beyond that and try like some of the things out of C++17, the compiler will take it just fine, and you'll now find places in the RTLs that were missing some support. There's things in, there's a C++17, like standard : file system or something. You can ask for file information as part of a C++ standard class, and it doesn't get the right answer. Don't do that. We have other interfaces in the operating system. Do that, and any open source code, you'd have to change that until we get it fixed. So again, some of the things we're looking going forward for the rest of the year. So if you look at the roadmap we have on the website, there's probably some place in there that there's another set of releases for all the compilers as we go forward. Like I said, it's all about debug information at the moment. Things about what to see. Batteries dead. Came back, but what to recharge this. The missing machine code in listings, so all the alpha and ITAM compilers, you ask for / machine code, and the gem code generator would tell you at this, while it's making the object, here's also the same instructions, mostly in the listing file. They're not quite assemblable in the listing file, but you get all the instructions, most of the static data, a lot of some background information from the compiler. We want to tell you things. On x86, you don't. LLVM is really set up for, they'll generate an object file, or they can generate an S file, an assemblable file. They can't do both at the same time. At least I'm not a smart enough C++ programmer to put another layer of abstraction and run two separate classes inside of LLVM. I think it's a little too hard for me to do. So we've been using analyzed object disassembly. We've added some support. It knows how to do lines, numbers. The Itanium one does not. The x86 one does. And I'm going to put some more stuff in there. I'll let the analyzed object disassemble know more about static data and some symbolization. I think it can pull that out of the dwarf. I think it can pull it out of some other data structures we generate. So I don't want to be poking into LLVM any more than I have to. Right. One of the things that it's going to allow us to do is have faster changes to pick up newer LLVMs going forward. Right. The one we're using now is based on LLVM 10, which is, I think it's modern. It's just a couple years old. The current LLVM is 20. So they jump versions quickly. There's a lot of new features. And remember, I told you I have 200 developers essentially across the planet. They add things to LLVM quickly. They've added some changes to the code generator, the optimization, tracking all the new Intel variants of things of x86. Obviously, other things in LLVM for other targets are not interesting to me at the moment. But we have today, we've already been working on bootstrapping our native compilers from LLVM 10 to LLVM 20. I have a claim that runs right now. That's LLVM 20 runs on VMS right now. Building everything natively. We can build now, stop using that crazy Linux cross compiler thing. I think we can build Clang based on LLVM 10 today, build it natively on VMS using the Clang that we have built on VMS, so it compiles itself. Uses CMake to do it. We ported a version of CMake to VMS to do it. And then ironically, as fast as LLVM changes their version number, they change their CMake requirement just as fast. So the version of CMake that's required for LLVM 20 is newer than the one we ported. So I have to go back and report it again before I'm able to natively build it again on it, because they see a new feature and they want to start using it. So I've mentioned this before, we are looking at some stuff to get, thread local storage. pthreads does have an ability for every thread. You can ask for some thread specific data area, and it'll have you a pointer back to it. And it's up to you to manage that. You can record news, but C11 and some C++ stuff, there's keywords in the language. You can say, have a variable and you can say thread on it, or under thread, or I forget the syntax, and you've asked the compiler and the backend, I need, data in this module that is thread local, not routine local, not process application. So that involves work in various tools, namely the linker, image activator, debugger. The list is about 10 long to do all of it. So we're looking at that. And then LLVM comes with a whole bunch of sanitizers. You can run it through and it can do type safety, memory safety. There's a bunch of things to look for free after use. Those are useful. See if we can get those enabled and port over. I was going to wait for LLVM 20 because I think that there's a better set to port over. And then LLVM 20 also finally has support in there for stack smashing protection, where the prologue routine would put some magic cookie in some place on the stack, and then the prologue would get it back and check. Of course, to do that right and to keep the bad guys away, it can't be a hard-coded symbol. I can't put, VMS is great in a string on the stack and check it at the bottom, because a bad guy would figure that out and keep that in place. So if you're going to have a buffer overrun or stack overrun, that thing that gets saved in the prologue and epilogue tends to be random. But it's not random per routine. I think it's probably I'll probably have it random per process. Makes it easier that way. But that's what LLVM and Linux boxes do today. I'll just do the same thing that Clang does and GCC does. They all did the same thing. I'll just do what they did. I probably can do that in most languages since it's LLVM. I think could I have this protection in COBOL? So buffer overruns in COBOL are kind of hard to do. But other languages like the legacy C compiler don't have to use Clang to get it. Maybe could do buffer overrun checking and the stack smashing for legacy C or Pascal or Flickr. Not sure about macro. I think at this point, that's the end of the slides about the compiler futures. I was thinking there was something else I wanted to mention. I think once we get the compilers for the schedule for the LLVM 20, we have compilers in the roadmap for the end of this year. I'm still not sure whether they'll be LLVM 10 based or LLVM 20 based. If all goes well, standing here today, I think we can probably have them using LLVM 20, and I would release all of them to freshen them all up. I bet we haven't done any of the testing yet. So we might bump into something that's going to make us have to go back into LLVM and re-engineer something, because going from LLVM 10 to 20, guess what? They've changed a lot of places inside the back end. So many of the things that we did for LLVM 10, some have easily ported over, merged. Git does a good job merging them all over. Some of them we've had to totally re-engineer, but at least this time around, like the second time, we know what we have to do now, as opposed to the first time we just kind of were wandering around trying to figure out what's the right thing. Now I know what the right thing is. So that's kind of where I see where that is. And then also all this code that we've changed in LLVM, I mean, LLVM is open source. Have I pushed anything back at all into the LLVM repositories? It's Git, so there is actually no repository per se, but it's in the cloud. Not yet. I want to, but certainly for the LLVM changes, there's nothing that keeps me from giving them to the community today, right? And I'm happy to make these packages. If you want to get a LLVM backend, then you can go. You want to play around? Anybody want to grab the Rust front end and slap it on a backend that's for VMS? You want to grab an Ada front end and slap it on a code generator. There's really, right, there's, unlike other places in VMS we've talked about where all these things have HP copyrights, there's no HP code in any of this. I mean, the stuff we've done to LLVM is VSI typing at the keyboard, right? So there's nothing that would prevent me from doing that, and I think we should. I think we should take that, all these LLVM, the ones we build, LLVM comes with a handful of tools. Again, it's all open source. We haven't touched a single line in some of these tools. You just recompile them and go. But the other changes we made are VSI only. Right, so I'm looking to try to have that distributed somewhere on the website somewhere later this year. So if you want to be your own compiler developer, you can do it. Okay, I think any other, so let's go to questions. How about that? If I got that. Rob has a question. When is BASIC going to have unsigned integer?
No. I've got a question for the audience here. For folks who are doing work on x86, is anyone still using a cross compiler?
Oh, yeah, I should ask. So
That's good.
Okay. Yeah. Early on, yes, right. People were using them. If you have noticed, they don't ship anymore with the operating system. 923 doesn't have cross compilers. If you have old ones and you think you can be lucky and use them, stop. Or if you have objects or images built by cross compilers, you may think they're running today. They probably are, but if you can recompile them, you'll get better code, you get faster code. So the cross compilers were a stepping tool, not an ultimate solution. I say your hand.
Do you have any plans to support decimal floating point?
Well, I mean, whatever you get out of Clang has all that decimal floating support in it. Do I need additional changes in the library? Probably.
There is an Intel library in C.
Yes. Yes.
But porting that onto VMS has been entirely driven.
I'll keep that in mind. But no, we haven't. That's on one of the many things on the list of what's missing in those RTLs. And I'd have to look particularly on that. Yes, it's free and open source, but I don't know what the license is on that. Okay. Same thing with math library stuff. I mean, our math library, again, on alpha and well, On Itanium, the math library is full of handwritten Itanium assembly routines that we got from Intel. On x86, I've just got a bunch of the reference code that we use for the portable math library that we have on Alpha, which is tuned great for Alpha, but those algorithms, like there are probably higher performance math libraries available for x86 with a somewhat reasonable license. I haven't looked at those yet. Though we did find that natively compiling the math library made it much faster, right? The optimizer helped us a lot. Sure, you wanted to.
I have two questions.
Yes.
Easy one, not easy one. First, do you think about pushing back what you have done on LLVM to the large community? The first question. Second, I just thought about a strange thing about motif, and with time we use some color characteristics and so on to use from VAX, and we translate it to Python. You retranslate it to Italian.
Yes.
And now if some application needs that, and so
there is no binary translator. That's correct.
Yeah.
That's the easy one. The other one is, have I considered pushing there, because they're both easy. That one just answers no, we don't have. I understand the need for a binary translator. Certainly, you know, if you don't have the sources, you lost them on VAX. If it did it because I wrote it for high performance on VAX, the two translations are probably going to undo all that high performance aspect of the code. For sending things back to LLVM, for the backend changes, I probably can. You know, it's just another target in their multiple target backend. With VSI, we have to provide probably a build system or something from the build against. They have this entire build farm that they use. But for Clang, it's almost certainly, I think the Clang community would be kind of not happy me, you know, pushing all this stuff of listing files and double-sized pointers and everything else back. It would just make the code more cluttered for the industry that nobody cares about. I mean, the code we've done, the changes to LLVM, the back end, I doubt if we've changed more than 1,000 lines in the whole back end. Not much at all. The front end, we've pounded a couple of places. We pounded on it pretty hard with a rock. So to get some of this, so they would be less likely to swallow those changes. I think those will probably always have to stay out of tree, and we'll have to just keep merging them for future claims.
Two small questions. Do you have any comments about performance and what you're doing in terms of the different, you know, new versions? Are there any improvement in the performance of the output?
Certainly, yeah. I mean, well, the answer to that first. Certainly, the optimizer makes a change. The difference between LLVM, LLVM 20, I haven't looked yet. There'll be a difference. I think most I'm looking for is functional differences and not performance. But yeah.
Secondly, are you using AI to actually do the review of your code, or
We're not. I'm not using AI. I can barely. You know, I don't have an easy way to show. My head's in a jar somewhere, so we have to be. There's AI for me. No, not. The trouble is, I mean, I can, you know, since a lot of the code that I have, well, at least it's stuff inside of LLVM, that code is well tested by thousands of Linux systems all of the time. So our code is, we review those changes in LLVM quite well. Other things in code, I'm certainly not going to give AI some random macro or bliss code, but I don't have a lot of that. But that'd be fun, I think, that when AI writes bliss code for me. Yes?
We were talking about listing files. The only time you actually use listing files is when you get a traceback and you get a line number in the traceback.
Yes.
That does not relate to the C file, because you kind of merge the
VMS historically is a listing line oriented system. Well, for a while it was, but I mean, historically the tracebacks are listing on numbers. In the debugger, you say set break on line 10,000. You say listing line number. You don't really say source file, source line number. So we've done that. Would you saying you'd like me to provide an option to let you do source numbers?
No, just.
I know.
This happen, if you, why do we need listing files?
I know,
If
I
you
know.
change this, you need
If-
listing file.
Again, it's also, and it's where the debugger has to know both at the same time, because of course it has to show you the source. It actually needs to open up the actual source file and go to line 10 to display line 10,000 to you.
And the feature in the listing files is the show structure layout. That's what we use it for.
Yes, almost every language does have that ability, show structure layout in Pascal. That should work just fine. C has a symbol one, Fortran has a similar one. I think that's great. Again, I asked back in the Clang world, I said, is there an option on go to your Linux box and whether it's GCC or Clang and say, I've got this weird struct I defined. How do you actually lay it out? I'm curious. Show me where all the fields went, where the alignment, and you'll have a hard time tricking the compiler. There are a couple internal document switches to Clang, and it'll dump out some internal representation of structures, which are meant for compiler developers, not for normal people. So that's hard. And again, some people are like, why would you want to do that? Because I may want to pass them across multiple languages. And I want to, I mean, as a human, we're back to AI testing versus human testing, right? If you're here at the end of the last discussion about Volvo cars, I mean, yeah, you can test automated you want, but you sometimes need a human in the process to double check finally that you've got things in the tested right. So yeah, but I like listing files. I'm trying to tell people at LM conference that they're great. Wouldn't you want them? No, no one seems to like them. I don't know. Yes.
Say that it's a listing file is also useful for.
Yeah, it's early on before the debugger was working. Many of us we debug with Resident Delta X Delta and having a listing file or analyze object disassemble file in the window next to us while we're doing that. One of the reasons, I mean, that we've had to put in the line numbering stuff into analyze object just to actually help that Delta debugging with listings. I tried to convince, my girlfriend to install an LP29 into the extra bedroom, but just so I can get real listings, but no, don't have room for it. Again, some of you people here know what an LP29 is, many of you do not. Big line permit. Any other questions? Okay, thank you.